Oh yeah, the one. Yeah, 21 or 2 or 3, rather if you use the Wi-Fi 1, 2 or 3.
Okay.
Yeah, friendly and the yeah, 1, 2 or 3. Yeah. There are 3 more changing passwords, so I think here is number 3.
Yes. Thanks.
Is it okay?
Do you want me to start? Good. The recordings broadcasted. Oh, great. Perfect. Okay, so welcome everyone here in the room, and also welcome everyone at home to this third OpenGeoHub Summer School Day, where I will say something about a number of things happening or recently happened in our spatial packages that I'm involved in. So my name is Edzer Pebersman. This is what I'm going to talk about. So the first thing I'm going to talk about is about spherical geometry. As I announced in the Mattermost yesterday, we went through the first 3 chapters of the book Spatial Data Science that I'm writing together with Roger Bivand. We will now go through the next 4 chapters, and again, this is the next 3 chapters. Again, this is essentially 3 weeks of my course, which we compressed to 1.5 hours. But it's okay. So you can do that.
Sorry, there is
Yes.
a request if you can use the microphone.
Sure, I can.
This is the one that you can wear.
Yeah.
If it's
Let's see where it goes.
this way.
Yes, that's right. And then
And you just do, yes.
like this.
And there's one.
Of the ears. Oops. Oops, it fell down. Hang on. Maybe this is. That was too rough.
Let me just.
Yeah.
Yeah. Yes.
Well, you say yes, but it's still.
Can I just move this?
Yes, please.
And this one should be this way.
All right. It's still
Thank
hanging.
you.
Okay. Oh, I can hear myself also much better this way. It's good. I don't know what I'm saying. Spherical geometry. Spherical geometry is a topic that I don't know why I ran into this, but world maps, right? Global data. So at some stage you look at world maps and you think, all right, we're going to plot these things, and then you think, something is not okay, right? Like like this typical plot is that we basically plot things, for instance, in a plot carré projection, yeah, with the two squares, the 0 to 300 minus 180 to 180 longitude and plus minus 90 latitude, and things are not exactly like that. And I ran into this quote from Nick Chrisman, who wrote this in 2012 when reflecting on the field of GI science. And there were two things that he said. One of the things that he said, one of the bigger things that he said is there are too many false conclusions drawn and stupid measurements made when geographic software built for projected Cartesian coordinates in local settings is applied at the global scale. Yes, and it's essentially what we're doing all the time, because we have all kind of software that uses these things, and we're going to do geometrical operations, and we think, how is this going to happen? Oh, we have this GEOS library. Okay, let's, this worked yesterday, so it will probably work today, and let's try that, and so on. And we throw things in, and sort of half consciously, but usually trying to ignore the fact that everything there is done in 2 dimensions, yeah, meaning in flat and planar space, which is okay for for spatial data, for geospatial data, if your area is relatively small. The larger your area becomes, the less it has the shape of something that is flat, right? So you can, of course, flatten it. You can ignore the problem and say, well, my geographic coordinates are Cartesian coordinates, yeah, and that is basically what you do if you say something like they take the natural Earth data, and then look at the NE natural Earth countries, and then I want to have my I'll just, and then I have to say something like return class is SF. If I want to have my data as SF, I'll just make my screen a little bit, my font a little bit larger, and for myself, give a little bit light. So we can get the natural Earth countries as any countries, return class is SF, and then we can load SF and plot for instance, the geometry only, not the it's just the geometry, and then we get this, right? This is what I mean with, this is what I mean with, yes, this is sort of not how the Earth looks, right? This is not sort of how world country data looked as they are, as they are stored or provided by this natural Earth package, and by most of the packages that provide global country boundaries. And this is how we then plot it, right? So we plot it basically with an aspect ratio of 1, meaning we get the plot carré projection. And of course we can project it to an equal area and so on, but nevertheless it's the same data we get. And basically what we see is that there's a hard boundary here, so that this area is cut. Of course this continues here, yes, this is a continuum. And there are the Fiji Islands somewhere here, so small that we don't see them, but they're also cut because they are unluckily, they happened to end up on the anti-meridian. And here we have Antarctica, which stops here and then goes to the South Pole, and then there's a boundary sort of all across the South Pole from east to west. Yeah, this is a point essentially, and then going up here again, right? So this is again one of these features that you need if you want to show it like this in a projection like this, and not otherwise. So yeah, so that is fine, and this has basically this has been the way that I think that GIS has done things, starting 50 years ago and never changed. Yeah, never went back from its path of doing it this way. Yeah, for some reason, and we're stuck there. And then a number of actors came up that had global data sets, and they didn't like that. They said, no, we're not going to compute distances from here to here or something like that on projections. Like we can do that. We can do these things on the sphere. So several libraries came up and were open source were provided. For instance, the S2 geometry library that was published by Google and used in all the Google products like Google Maps and Google Earth and Earth Engine and these kind of things. There where basically the model was that of points on the sphere, and the geometries were sort of modeled on the sphere instead of on the plane. And that is a different thing. And we started using this library. You can see that here when you load SF, you can see here that it's using S2, that SF use S2 is true. Yes, I can also switch that off and say SF use S2 is false, and then I will not use it. That means if I have geographic coordinates, I will just assume that they are flat, they are in R2, they are flat, two-dimensional flat coordinates. And it means that I'm using another library, that I'm using the GEOS library. Yeah? There was this figure that Jakob also showed earlier. Here, where you can see what the sort of the libraries, the underlying libraries for doing the complicated stuff. I mean, SF is just bookkeeping. The real complicated stuff is in all these libraries. And one of the libraries is GEOS, that is basically used by pretty much all the OSGeo software. It's an OSGeo library that is used by PostGIS, by Quantum GIS, by GeoPandas, I assume, by Python, as we saw, by Jupyter, as I saw yesterday. And there's another library called S2 Geometry that is an open source library developed by the Google engineers, used by all the Google spatial, Google BigQuery GIS uses it, Google Earth, Google Maps, Google Earth Engine, and so on. That does things as they are. Well, they are not. I mean, they do things on a sphere. Of course, the Earth is not a sphere; it's an ellipsoid. But the ellipsoid, the sphere, the shape of the Earth, the ellipsoid, is much more similar to a sphere than to something that is flat. Yes, and that statement is, I mean, drastically more similar. Yeah, not just a little bit. For instance, they are both round, the sphere and an ellipsoid. Yes, a flat plane is not round. So this is sort of an extreme thing. And the question is, when does this get annoying that you're doing things on the plane? Of course, if you look at the history of PostGIS, they came up with, like 10 years ago, with a type called geography. Yes, they had a type called geometry, which is the simple feature geometry, which is implicitly assumed to work in 2 dimensions, so not on a sphere. And then they came out with a thing called geography, and that could do all kinds of things that worked on spheres. Yeah, that could work with round things and so on. So like distances. Yeah, it could compute distances over the sphere. Yeah, which is a very different thing. And a number of other things, but there were a number of things it did not do. For instance, it tried to do buffer, but then it would look at where am I, and then project things to a proper or somewhat proper UTM, and then do a buffer and go back or something like that. So it was kind of sort of a relatively unfinished activity. Funded, interestingly, by the way, by Palantir. I don't know who of you is familiar with the company Palantir. Yes, Palantir are the real bad guys, right? So the sort of the aggregator that aggregates all the network and search information from everyone and profiles things and writes your complete profiles and sells them to the advertising companies. Yeah, that's the kind of. So they had these global data sets and wanted to have a database that could deal with geometries without them worrying about having to project things locally or something like that. Yeah. So anyway, that was what PostGIS did, and now we have this S2 geometry and link that to S2. And basically, when you do things in SF, then almost everything that deals with geometrical operations that I talked about yesterday, distances, but also intersections and areas and so on. Buffers is a bit of a difficult and different story that this seems to be now gets a proper implementation in the future S2 geometry. So why does this matter? So one thing that matters is that that by doing this switch that I just said, switching S2 on and off, you basically swap to doing everything, you tunnel everything to the GEOS library, to the, or you tunnel everything to the S2 library. Yeah, of course, this is only, that I'm talking now only about the case where your data are not projected. Yeah, so the natural Earth data set that I just imported, as you can see, has a coordinate reference system that looks like it's terrible. It still uses proch4 strings apparently. Yeah, but if you can read them, you can see that this means, this essentially means that these data are not projected. Yes, they're unprojected. They're longitude, latitude coordinates, geographic coordinates. And the package should really do something proper and return a data set with a proper, not using proch4 strings. So only if that is the case, then of course the possible switch to S2 is being used. Otherwise, it's not. If you use projected data, anyway, you were thinking of a flat space. You projected your data to a flat two-dimensional Cartesian coordinate system. Yeah, so only then this plays a role. There is a couple of things that, of course, since these two libraries, GEOS and S2 Geometry, had entirely different histories of where they came from, there is not a one-to-one correspondence. Yeah, so there's a number of things I mentioned yesterday. The nine-dimension extended intersection model, and the way you can sort of get these relationships, the ST relate between two geometries in terms of insides and boundary and exteriors of pairs of geometries. That is something that is in GEOS that is not in S2 geometry. So they took a relatively fresh approach to, as you can assume from Google engineers, to the whole problem, a very mathematical approach, and not one that first started looking at simple features or something like that. Yeah. So we had some, some challenges of putting that, sort of matching that to exactly what SF does, which was very much inspired by what GEOS did historically, but kind of managed to do that. So consequences then are that we don't have a one-to-one mapping, that sometimes things look different, but the main thing is basically that we have a different concept of what a straight line is. Yes, as I said yesterday, we have simple features means that we don't work with curves, parametric curves like Bezier curves or functional things, but that we work with straight lines between sets of nodes, right? We have nodes and edges, and the edges are straight between the nodes. That is our assumption. We don't even talk about it. They're just straight. But then what is straight, right? And straight, if you have large distances on the sphere, and you draw a straight line, it would go through the Earth and not over the Earth. If you want to have it go over the Earth, then taking the shortest path is what we call a great circle segment. And that is not something that is what you do if you would sort of linearly sort of interpolate latitudes and longitudes. Yeah, that is something entirely different. Yeah, if you linearly interpolate longitude and latitude, you would have 2 points on opposite sides of the pole, at 80 degrees north. Then you would sort of follow the parallel. If you would take the shortest path, you would cross the North Pole, right? So it is entirely different. Of course, especially there, but in principle everywhere where distances are a little bit larger than trivial. Yeah. So this is one. This is one big thing that the meaning of straight is suddenly different. So things that then basically, if I have a square area or an area denoted by 4 points that is relatively large, then and a point falls in it in R2, then it doesn't have to fall in it on S2, right? Because it's a different area. We have the straight lines follow a different path now. A nice complication that a lot of people are not aware of is that what is it called? Request for RFC. That the JSON format, in the way it is defined, it was defined by Howard Butler and other people in 2016, is that the JSON format tried to make a number of things easier, yes, and also tried to make a number of things explicit, and it did that, and very few people realized that. But one of the things it made explicit, one of the things, as we all probably know, is that all coordinates need to be associated with the WGS84 datum. Yeah? And a lot of geodesists today say, well, WGS84 is the thing we have to get rid of today or as soon as possible because we can do better. Yeah? So there is one issue where you say, okay, well, this was, early 2010s that this sort of came into being. Another thing is that that it has very specific, explicit statements about, and I have to look that up, about the connecting lines. 14, yes, the connecting lines, yes. So we have here, for instance, connecting lines between pairs of longitude and latitude basically follow this path, right? And we have other places where it defines. Let me try to find this text, multi-line string. For instance, here it defines what a line string is, yes, and it defines here how points on a straight line between 2 points are defined, yes, and you can see here that this is what you do in R2. Yeah? This is basically following the straight line as if latitude and longitude are orthogonal Cartesian coordinates instead of being spherical angles of points on a sphere. Yeah, so it says the points of this line are the points according to this equation. Yeah, so it gives you a definition of a straight line, which is not the great circle distance between points, but which is the straight line in this space, yeah, which is the flat space, and not the curve, not the spherical place. So if you would follow this definition, yeah, and you would import a GeoJSON file to a data system that does its geometry on the sphere because it's global data, or just because this is a good idea in general for spatial data, yeah, because you don't have deformations, then you basically would have to add nodes. You would have, for every line segment, you would have to use this equation to add nodes to every segment to make sure that you're following this path and that you're not taking the great circle path. Yeah, that you reduce that error if distances are a little bit larger. And this is something that actually BigQuery GIS, sort of the big Google spatial database, does. If you import a geo package, it will not do this. If you import a GeoJSON, it will do that. It will add nodes to lines so that your lines are the lines according to the GeoJSON definition. Whether you are aware of this or not, maybe it's an option. But this is something that, we tend not to think about straight lines between points, but they're ambiguous. That is the issue. And different software does different things with this. There is an excellent blog here from Dewey Dunnington about an update on this S2 package that he did recently. He basically wrote everything. Here you see an example of exaggerated example of a data set that basically where you think that, okay, this is a self intersection. But this is plotted in R2. If you plot it on something that's more closely reflecting what is happening on the sphere, you see that it is not self-intersecting, yeah, because this is a great circle distance. So, and here is another example of how things look in R2, the black line, how they look in S2 and in the red lines. Yeah, so we get a strong difference there, especially if you have larger distances. So this is one issue. Another issue with spherical geometries that I mentioned where I mentioned yesterday that whenever we have polygon data, that these polygons, before we can do anything with geometry libraries, these polygons have to be so-called valid. Yeah, that means that polygons don't have self-intersections, or there are all kinds of things. The figure 8, for instance, right, would not be a proper polygon because you cannot tell what's the inside or what's the outside. So we have the problem of validity of polygons, and the thing is that, as I mentioned here, this is sort of this polygon of the of Antarctica, as an example, is has this intersection to the South Pole here, and then goes back through, what is a point, what is the South Pole, goes back to plus 180, minus 90, and then goes up again, right? Which makes the polygon valid in R2. So we need that in order to fill it, right? To color it, we need that, but only on this type of plot. If you would do a polar plot of this geometry, so look from the side of the South Pole, you would find something like this, right? So this is the polygon that we're looking in, which is valid on R2. But if we look on it as it is plotted on the sphere, we basically go here to the South Pole and then remain at the South Pole for a long time, for a lot of nodes, and then go back to the identical point and continue it, right? So we have this little feature here when looked at this polygon on the sphere, which invalidates this polygon, right? Right now it's an invalid polygon, so we cannot work with it. So if we project this to a polar projection, or just look at it on the sphere, then this polygon is invalid. This polygon, as it comes from natural Earth, is invalid. Yeah, so to work with it, we have to first make it valid. And the other way around, we have polygons that are valid on the polar projection or on the sphere. And if we would look at it in a plot carré, in sort of the standard, latitude by longitude plot of the Earth, it would look like this. And it is invalid because if we zoom in here, we get these self-intersections. Yeah, we have something that doesn't you cannot draw this line. That's why we have to make this excursion in R2 through the South Pole. So we have this thing of polygon validity, which cannot be true on both worlds, right? On R2 and on S2. So here we have polygon, there's a number of polygons. This is one. Another example is, let me just see if I can easily find it. Another one is the Fiji Islands, which is here in a highly generalized way. I don't know where this comes from, natural Earth countries, which is plotted here, where we have, at this point, we have the anti-meridian, yeah? And that is also what the GeoJSON definition, for instance, prescribes. It says, if we have anything that crosses the anti-meridian, we're gonna cut it there and divide it in two halves, on one side and on the other side, right? That means, on this view, we have a little piece of the Fiji Island here, and the rest of it we have here. And that's fine on R2, yeah? But if we look at it on a proper projection that does not have the anti-meridian as the split thing, but another other projection, or I look at it on the sphere, then we have something like this. And this is a single polygon. So this is again non-valid. Yeah, this is a polygon of two parts that shares a common edge, right? Which is an invalid geometry. So you can make that valid then, of course, but you have to do it. It's again another case where we cannot be valid on R2 and S2 at the same time. Yeah, S2 referring to the sphere, R2 referring to the flat Cartesian space, two-dimensional. This is, of course, nasty, but it's life. Yeah, this is the Earth that we live on. Yeah, it's round. So welcome to the round Earth. There are, of course, groups that discovered that and found workarounds. So there's Natural Earth that does this and says, well, I cut it at my plus minus 180 exactly. And there are other groups, like if you load the world country boundaries database from Eurostat, from GISCO or something like that, they also have all kinds of administrative data. And download that, I think it's also GeoJSON. Then you will find that in the Fiji Islands, that they dug a canal, yes? So they made here two polygons that don't touch each other. Yes, one, this one ends at minus 179.999, and this one ends at plus 179.999 or something like that. So they have a little space between the two polygons, which of course solves all your problems, right? So if you then project it to a projection that looks at at the antimeridian as the middle of your area or something like that, so a proper projection for the Fiji Islands, you might note it, right? You might notice it and if you zoom in, you see the canal between the two islands, which is not there. But yeah, so you can fool around with these things, at least for the antimeridian. I don't think you can do it for the poles. But of course, those are your kind of your singularities and where things really go wrong. Right. So those are the basically the takeaway messages on this whole thing with spherical. So the larger your area is, the more an incentive you should have to work with spherical geometry, because it is a much better representation of true geometry than the flat sphere is in all respects. Yeah. There is then the ambiguity about what straight lines is, which may become an issue, because you doing this or doing that, you find different results, because the straight line is no longer, the geodjacent defined straight line is not a great circle distance, which is what S2 geometry assumes. There is no general validity. Yes, polygons can be either valid on this world or on this world, not typically not on both. Those are the three take-home messages. There is actually two more things that I only sort of really discovered when reading into this S2 geometry stuff, which was a very sort of interesting and refreshing adventure. One of them is that I mentioned yesterday that we have simple features where a polygon is defined as an outer ring followed by 0 or more inner rings, and the inner rings are holes in the outer ring, right? This is how it's defined. So we have a polygon which is an exterior ring that may have holes or not, right? So that's it. So the outer ring is clear, right? Now the outer ring, that means an outer ring has an inside and an outside, right? Which is unambiguous. Which if we think R2, we think flat space in a polygon, right? That is what we see, that we look at the screen and so on, that's it. So it's clear what is here, the inside and the outside. However, if you think of the surface of a sphere, then any polygon on a sphere divides the sphere into two regions. Yes, one region and the other region. So you could say the inside and the outside, but it's not sort of on R2, it's unambiguous what the inside is, because the outside is infinite, stretches to infinity. So we have no difficulty in saying what the inside or the outside of a polygon is. But on a sphere where there is no infinity, it's a finite surface, any polygon divides that surface into two parts. So you have this thing about, okay, what is exactly your inside and what is your outside? And there you need to, it's not sufficient to say, well, this is the first ring which tells me what the interior is of a polygon. No, this is ambiguous. So you need to look at a ring direction and, for instance, make crystal clear that the ring is winded counterclockwise, and that when I sort of follow the nodes counterclockwise, that everything on my left hand is the inside. If I would know that the other way around, this way, then everything on my left hand is here is basically the polygon, right? And this is the non-polygon. So basically, this is now a hole. So I have a single polygon where I thought this is the inside. It's now the hole. It's the rest of the sphere that I mean. Yeah. So we have on the sphere we have suddenly a different meaning of polygons. Yeah. Polygons are suddenly can mean the other thing. That is one. So that is one thing. So suddenly ring direction is essential, and you would be surprised at how many data sets you run into where the noding is the other way around as you expect. Yeah. So although simple feature standard says that outer ring should always be counterclockwise noded, you will be surprised how often that is not the case. Yeah. And GEOS doesn't care. Right, so everything, QuantumGS, PostGS, all your software works without notifying that you have a ring here with a wrong direction. Right, nobody will warn you up to the moment that you run in the case where it matters. Yeah, like here, and suddenly you look at the whole world instead of your country. The rest, you look at the rest of the world. Yeah, so there is different ways. So I think Google BigQuery.js by default says, I'm going to look at what is the smallest region. Yeah, so there's always two regions. Like for this island, from the Fiji Islands, this is a very small region. The other region is the rest of the world, is very large. Yeah, so I'm going to look at what the smallest is and assume that that is the inside. So assume that all my rings are wrong and that I'm going to revert them whenever one has an area that's larger than the half of the sphere. Yeah, that's one thing you can do. That means assuming every ring is wrong and correcting that, and nobody ever comes with a polygon. That is most of the world. For instance, the polygon of all the oceans. And the other way is, of course, that you say, well, take care of this and make sure that your data are correct, and then assume that they're correct and proceed with that. That is one thing. So there is suddenly something like the rest of the world polygons. Another thing is that we had in the yesterday's lecture we talked about the empty geometry, like a points empty, which is basically a geometry for which there are no points. Yeah, it's an answer to a query for a geometry with no points. Here in S2 we have another type that we didn't run into yesterday, and that is the full polygon. Yes, so in addition to the empty polygon, no points, we have the full polygon, which is all points. Yeah, so the whole sphere. Yeah, so and that's an extremely useful thing if you have, for instance, the country boundaries, and from here you want to find the oceans. Then you need to do the difference of the full polygon, the full polygon, which is the full polygon on entire Earth, minus the countries, is the oceans, and you end up with the polygon reconstruction of all the oceans. Yeah, and this is something that is sort of working with ocean data is something that is where GIS is typically not really made for, but you can do this properly if you have the proper sort of software. And I think working on the sphere is the first thing to do there. That is one thing. Another thing you would do is, for instance, buffers, and we have done blocks where we give examples of this buffer with sort of all the regions that are within 200 kilometers from from a coastline or something like this, and computing the area of that is something that will be extremely hard to do reasonably and with flat software, right? And with S2, this is basically standard. So this is one. Aspect that we looked at, and with support. I mean, this is one thing that causes a lot of annoyance, right? Because it breaks workflows from a lot of people who say, well, I had this data set and I ran this 5 years ago, and now I run it again, and it crashes, and it gives me all kind of cryptic error messages and so on. Yeah, that's because we used to do things on R2, and apparently you had a data set where everything worked for that, which is the majority of the GIS data sets, I would say. And now you have to do extra steps, for instance, first make your polygons valid before you can continue and so on. So it's an educational issue, and it's also an issue that is, of course, difficult and annoying, since all the legacy systems, GIS systems, quantum GIS, PostGIS, and so on, dominantly work with R2 representations and want world country databases like this. Yeah, the way they are not. Yeah, meaning invalid polygons for things on antimeridians and poles. Luckily, we have only one Antarctica, and a lot of folks here doing global mapping studies basically throw out Antarctica because it's anyway unsampled, right? And nobody misses it when you leave it out in the world map. So I mean, your nature editors and so on will not complain if you give a world map but not showing Antarctica. This is sort of everyone got accustomed to doing that, whatever is the reason for that. Yeah. Good. So that is all I wanted to say about spherical geometries, and and of course, our hope is that. So I think it is a reasonable assumption to say, if your data are in geographic coordinates, you do things on the body, on the sphere, on the shape of the thing that you're looking at. if your data are projected coordinates, you're doing things on R2. You can of course project latitude and longitude to plot carré and do everything in projected coordinates in plot carré, which is what GEOS does if you do nothing. And I think not such a good idea. But you make basically that step an explicit extra requirement for users to make to see what they're doing. Yeah. Are there any questions? Yes, Jacob.
So I have a few, but maybe for the sake of time, I will only ask one. For now, so we are talking only about vector data, and what's your idea or vision for raster data? How we should think about raster data and spherical operation? Because now we can spot that for vector data we have two paths, and for raster data we have still one. So what's your comment or ideas about that?
Yeah, so that's a very good question. So I'll repeat it for the listeners at home. So I'm only talking about vector data here, and what's the case with raster data. I think, Jacob, that it is exactly the same problem you have with raster data. Of course, a lot of raster data you and I look at is remote sensing imagery, where we look at relatively small areas, and where we look at, tiles are 100 by 100 kilometers. So the curvature of 100 by 100 kilometers is considerable, but not that extreme that we really have to. We don't do compensations on the cell size. We think the cell is 10 by 10 meters. It's not, of course it's not. Yeah, but we do as if it is. Of course, if we had rasters of 1,000 by 1,000 kilometer, we could no longer do that. Yeah, so it depends a bit on it. The problem gets larger when your area gets larger, and also the problem gets larger when you look at 10-meter imagery over a continent. Yeah, then you get, for instance, for Sentinel-2, you get everything in UTM zones, and you have to put together different coordinate references in different UTM zones into one analysis, one data cube, which forces you to basically create a new raster structure over that, because the UTM zones don't match, right? So there's always problems. I think if you look at the communities that work with raster representations of larger areas, then you think of meteorology and climate. And people there all the time work with grids, with raster data, but never assume that the world is flat. Yeah, because your differential equations don't make sense in R2. Your differential equations only make sense on the sphere. So I think they quite often think that the Earth is a sphere rather than an ellipsoid. Yeah, but they don't think that it's flat. Yeah, so they are already working in that sense. And there you, of course, if you do a regular raster in longitude and latitude, you get these things at the poles. So what they'll constantly do is basically turn around the poles and say, put the poles at the equator so that my raster, when I look at the polar region, so that my raster looks nice, right? That my cells don't all touch in one point like they would on the pole. So they do all kind of funny things or standard things to address numerical issues that you would otherwise have with raster representations. But rasters are never raster cells are never square and of constant size. If they are about the Earth, then they're not. Yes, whatever, wherever it is. The Earth is curved and the raster model is flat. So the problem is there, and it can for reasonably small settings be ignored, and in many other cases not be ignored. Does that answer it?
Not entirely, but
okay.
I'll ask more questions.
Good. Ben?
We were just thinking that in the talk yesterday we saw the cube sphere, so kind of approximation that we would like to use in the prediction. So instead of having the Earth feeding in the flat surface, we put it into the cube, that you have 6 sides that can approximate flat surfaces.
Yeah, that is.
Still a proxy, but
yeah, that is. So let me go to S2 geometry. They changed this. This is basically what S2 geometry, the library, does. So whenever you work with a spatial geometry, one thing is that you do the geometry correctly. The second thing is to make things fast, you want to work with an indexing structure. So indexing structures always use some kind of rough estimate, some rough sort of approximation that somewhat reasonably works. And S2 geometry also does that. It works with a cube, with cube faces representation. Let me see this thing here. It is. Yeah, these are the 6 cubes that are sort of the first indexing structure, and then within these cubes you do this space filling curve, this Hilbert curve that sort of refines endlessly 2 index points within space. So they have an indexing structure where the first 2 bits tell you which cube phase you are in, and then increasing bits tell you in increasing precision on your index, your coordinate on the Hilbert curve, yeah, where you are on the Hilbert curve. So this is a very clever way with a 128-bit integer. You can, I think, represent things at whatever centimeter level or something like that. You can address Earth locations with centimeter precision. So this is one way. Another way is that you do a hexagonal, so that you do an octahedron representation or a football and so on. So that is what, for instance, Uber's H3 library does, which came a couple of years later, but that has this sort of hexagon indexing structure, which is, of course, better fits the Earth in the sense that the cube is sort of less good approximation of a sphere than an octahedron is. So there are different ways of doing this, and S2 does it also in one way or the other. I'm not sure whether, how essential that is that you do one or the other. I think the main thing is that you have a spherical model primarily. Yeah, so other questions? Raster. So Raster, well, thank you for starting. I was just going to talk about raster data. Raster data in R, I'm not going to sort of give a complete overview of what happens there, and those of you who saw Jacob's presentation know that there is a package called Raster, which has been there for 12 years, and now a new package that succeeds it called Terra, which does things very well for raster data sets. I'm mostly interested in looking at a slightly different representation of things. And that is what I do in the package stars. And package stars is a package for data cubes, yeah, for spatial temporal array data. Yeah, so array data. So we saw that yesterday in Martijn's presentation that Julia, for instance, also reads raster data in arrays, right? Arrays are the natural sort of layout of numbers, yeah. So you have vectors, but once you have an image, you basically have a 2-dimensional array. Basically, you have a matrix of values, right? And then you can have several colors of an image. Yeah, images typically RGB or multispectral images have like 15 different bands. So we basically have, for every raster cell, so to speak, row and column of a location, we have the same set of color values. Yeah, so we have a 3-dimensional thing. And that is also the model that that Raster and Terra deals with. Yeah, raster data sets for which we have a handful of them associated with typically with different variables and different colors, maybe with different times. And so we call that a raster stack. Yeah, so I think raster stack is I'm not entirely sure, but I think this comes from the package raster, which called it a stack at some stage and said, well, this is a raster stack. Now everybody talks about raster stacks. Thing is that the world doesn't end with raster stacks. Of course, this is the obvious case where we have a set of imagery that is time associated. It could also be associated with different colors, different wavelengths. Yeah, so I see it as a third dimension, not as sort of a set of these rasters, but really as a dimension, because this dimension can be ordered. Like this latitude and longitude are clearly ordered. if we have a set of different variables, like we have land use and we have geology and soil type and we have precipitation surplus and something like that, yeah, then of course they are different things. Yeah, they can be different different layers. Yeah, and that is essentially the original GIS model. Yeah, is that of okay, we have layers of things that basically denote different properties of the landscape. Yeah, they look at the classic GIS literature and so on. And there we have essentially a set of layers that could be raster or vector layers. But here they are raster layers with the same geometry. And my stack would essentially denote different properties. Yeah, so be unordered. I can also have something like land cover, but associated with different times. Yeah, so then I get a time stack of land cover. Yeah, which is also a sequence. And then, of course, the third dimension is ordered because it's time ordered. But I cannot have like a sequence of land cover and a sequence of precipitation. Yes, in a three-dimensional stack, right? If I stack those, I have a stack of things that are different land covers at different times and precipitations at different times. Yeah, so how are you going to handle that? So, okay, you might say, I'm going to do 2 time cubes. Yeah? Okay, but now you have like 15 of them, right? So the thing is that quite easily you end up with things that are more than 3-dimensional. Yeah? And in particular, the standard case is that of remote sensing, where we have for a fixed region, the tile, so to speak, that you're looking at, we have the raster dimensions, X and Y, we have a set of bands, and we have repeated observations. We have a time series over 5 years of Sentinel-2 or over 40 years of Landsat or something like that. Of course, 40 years of Landsat, you have all kinds of other problems, but you could homogenize that and try to make that one sort of 4-dimensional data cube. So the data model that basically Raster and Terra look at, the raster stack, is in that sense somewhat limiting if you have more than 3 dimensions, yeah? And it's not unlikely that you end up with more than 4 dimensions, yeah? It's not sort of exotic to have this, because I can have, for instance, this time sequence of Sentinel-2 and have another time sequence of Sentinel-1. Well, of course, that's not the same colors, right? This has different bands, but you can think of sort of extending things. Also there, if you look at what the meteorologists do, as we heard yesterday from Martin, is that they have different altitudes. Yeah, so they have layers for every altitude in the atmosphere, not just heights, but associated with pressure levels and so on. So it's not even easy what these altitudes are. But it's another, like, okay, we have 15 altitudes. So we have sort of this, well, we could have in the bands, we could have then 4 different variables: temperature, pressure, and humidity, and cloud percentage or something for every pixel. Then we have a time sequence. Then we have X and Y raster, and we have a set of altitudes, right? So we end up with a 5-dimensional data cube. So without any problems. And the thing is that life doesn't get easier, but it is basically the way we represent our data. If you need to work in this model, then the first thing you're going to do is throw out all your dimensions in some way. Yes, and then start analysis. Yeah, because this is your data model. Yeah, so what you're going to do is first throw out all the bands and sort of replace them with a single thing like NDVI. So I'm going to ignore these 15 bands, but work with NDVI. One problem solved. Yeah, 1 dimension gone. Yeah, nobody. I'm not going to think about it anymore. I'm just going to push it out and continue here because I don't want to have this problem. Yeah. But of course, that's a loss, because you throw away 13, but you ignore 13 bands, you take 2 and apply an equation to them, reduce them to 1 without thinking. Also, right? And then people could say, why do you do this? Why don't you work on this full data space? Good question. So quite often dimensions are seen as a nuisance, as something to get rid of before doing serious work. Yeah. And that is part of that is that we can't handle that, yeah, because certain software says, raster stack is the most complicated data structure I can represent. all kind of things you want to do with data cubes is for instance, it's selection you do, right? So here we filter, we say we go, okay, we can take one time. This is also a big solution. If we have temporal data, we just take one time issue. We take 1 year and then we work with that year done, paper written, and so on. Another thing is compute bands or select a region to reduce data sets. You can also apply all kind of functions on dimensions. Here we do low pass filters on spatial raster in some way, or you could do low pass filters on time dimensions and so on. So thinking of these dimensions as really sort of directions in your data which you could apply operations is a very useful thing, because a lot of the concepts like noise removal or whatever, it can either be done in a time dimension or in a spatial dimension. And there can be reasons to do one or the other, but you would like to be able to do both. Another thing is that we can reduce dimensions basically by throwing things together. As I said, here we can reduce the bands by computing a single index, for instance, the NDVI or the first principal component score or something like that. We can also reduce time. Let's say I'm going to do an average over time. I'm going to do a cloud-free composite, taking the median over all my time steps or something like that. That is another activity where I use all the instances of a dimension to reduce it in the next step, so that reduce it to a single value, but by computing over the dimension rather than simply selecting one instance of a dimension. Yeah, so this is, of course, this is richer. This is a standard activity. Another thing that happens a lot is that we want to aggregate or sample raster, what I call raster data cubes. So these things where my spatial dimensions are raster dimensions, and sample them or aggregate them to vector data cubes. And here is an example where I have, for instance, a region, and I want to get, for instance, the minimum of all the pixels in this region, or the minimum of all the pixels touched by this line string here. And for these two geometries, I want to have that full data, that full data in the sense of the band dimension and in the sense of the time dimension. And I end up with what I call a vector data cube. The vector data cube is a sort of surprisingly obvious data structure that surprisingly few people run into, or sort of, we have very little tooling of handling vector data cubes. I'm really curious, still have to figure out how these things work in, for instance, Xarray in Python. But I have a feeling that that is also very strongly raster oriented. And vector data cubes basically are also array data, but array data where we don't have raster dimensions X and Y anymore. So we don't have two spatial dimensions. No, we have a single spatial dimension, which is just a set of geometries. Yes, and that is something that is very easy to generate and very easy to reflect in the stars package. We'll show in a minute. Right, so here is another example where we have this data cube and we say, okay, we have a time dimension, but for instance, we could associate this dimension with my spatial locations. I have the sensor locations here, which are point geometries, which is a single dimension. Yeah, of course, the geometries are two-dimensional things, but they're single things. They're just a set. Yeah, they're an unordered set. Yeah, so I have this dimension associated with my geometries, and I could have another dimension associated with different variables. Of course, if you do that, then you get apples and pears in this data cube, because you get, you know, PM10 and NO2 will be 2. They have different measurement units, so you shouldn't do. But you could still, you know, compute multi-parameter indexes, right? Look at the parameter dimension and see, you know, how many times at certain locations more than 3 parameters, air quality parameters, exceed the threshold level. Yeah, you could do these kind of things. Exceedances, of course, then the exceedance levels should be, you know, it should be unique for each parameter. So you need to watch out there. Right. So that was basically what I wanted to say about data cubes. There is this package called stars that we work with. That is, somewhat a research project, but it's working nicely for a number of use cases, and that basically represents arbitrary array data with spatial and temporal dimensions, right? Where we can have raster dimensions, or we can have vector dimensions, or we can have combinations of them even. Yeah, so it is simply an arbitrary dimensioned array that we have, and so the data structure that stars uses is very simple. I do the same thing as raster does. Here, if I sort of start with nothing, then it generates for me a raster, sort of two-dimensional raster map with 1 degree, with a 1 degree global grid. What it has is a number of things. The object that I get, the star object, says I have 2 dimensions and 1 attribute. Yes, so it's again it thinks of attributes and dimensions. Yeah, so I can have like all the examples I showed with these data cubes. I have one attribute, right? My pixel is has the value 15. Yeah, it's a scalar. So my record, so to speak, in my data cube is a scalar. But of course, I could have several of these things, and they could have different types in R. Right? One is a numeric, and the other could be a factor, and the other could be a logical, and so on. So I might have multiple attributes, sort of instances of different type, that I then could add, as different attributes that would have the same geometrical properties. And here you see it is simply a numerical array, as you see, filled with values 0, right? And what then followed is the more interesting. So this is the payload, so to speak. It's just the array. Yeah, it's just a 2-dimensional. So it's a matrix, 2-dimensional matrix filled with zeros, which has these dimensions. And then comes the metadata, which is an attribute called dimensions, and that is essentially that holds the information about what do these dimensions mean, right? And it says, okay, I'm go from here to here. I want to keep that because I might do a sub-selection where I will not change my geometry, right? I could say, okay, now make a sub-matrix that runs from 100 to 200, something like that. And it says basically, how is this, what is the meaning? So what is the offset? What is the boundary of this X dimension? What is the boundary? What is the boundary of the Y dimension? And what is the step size? So in X dimension, it's 1. In the Y dimension, the step size is -1, because we typically go from images. We start on top and then we go down. So increasing my step means that my Y coordinate decreases. Yeah, so offset and delta basically tell you how to go from an index to a coordinate. Yes, it says first coordinate is 90, and then the next Y coordinate is 89. By the X, the first coordinate is -180, the next coordinate is -179. And this starts at the raster edge, right? So this coordinate space starts at my raster edge, not at the raster cells, not at the cell centers. Yeah? And then it has a coordinate reference system, which is the well-known text string with the whole stuff. And it has 2 more values, which is a logical that tells me, do I have like point values, or are these areas, are these raster cells? Should they be interpreted as little polygons with something like a constant or aggregated value? And I have a field called values, which might contain the geometries, for instance. Yeah. So that's happening there. Yeah, which is now, the values is now 0 because I can compute my values because I have a regular. Yeah, this is a regular layout of 1 degrees in this reference system, and I can see from offset and delta that I have a regular layout. Other things are, here is an, yeah, as I said, there's a couple of other raster forms that we can represent. Of course, if I have rectilinear grids, I no longer have an offset and a delta, but I need the values for all of these x coordinates and the values for all of the y coordinates, which is exactly what that formats like NetCDF and ZAR do. They basically, for every cell, for every row, for every column, they give the coordinates if it's rectilinear, and for curvilinear grids, they give basically rasters with longitude and latitude for every associated with every cell, in which case you can represent every possible crazy grids, like even these discrete grids or hexagonal grids and so on. So in principle, you can deal with them as well, but the tooling is sort of not easy to I mean, things like plotting is not easy to realize, and that's in that case if you have things like the hexagonal grid and so on, it's messy. Right. So so one of the goals of the stars object was to create a set of classes that can, or in at least one class and some extensions. That can deal with in-memory arrays. Yeah, like here we have an in-memory array because it's a small array where you can keep it in memory. It's just an R array, right? So it's a native R data structure that everyone understands and can deal and can handle with. Of course, there's a lot of data that you cannot, or that is very impractical to try to keep in your main memory. If you have a lot of Sentinel-2 imagery on your hard drive or somewhere, you want to go through that, then that's not easy going to work. So another model that STARS uses is that of basically out of memory or on disk rasters, where you basically say, well, here is the data set, and then it reads the dimension table, just sort of what's the sizes and so on, and it will not sort of load the whole thing in memory, but basically it just keep the file name of this thing, and then sort of postpone the work until you need to do something with it, like plot it or like download it or something like that. And then it's going to compute things, only at that moment, but do it chunk-wise, right? And the typically chunking is currently a spatial chunking, which of course is somewhat of a limitation. But that covers a lot of the use cases. Yeah, so that it means it will read a small area and then do the computations and then write the result. And then we'll go to the next area and load those data, do the computations, write the result, and so on, and do this chunk-wise. Yeah, so that in principle, if your hard drive is large enough, you could do arbitrary sized data analyses. Yeah, this is similar to what Raster and Terra do, but Raster and Terra do it in a, let's say, in somewhat possibly in a much more efficient way, but definitely in a less transparent way. Yes, because it has sort of more opaque data structures. The objects are basically pointers to C++ objects, and everything happens there. So it is harder to see what is happening if something goes wrong. Here it is relatively easy to see it because the entire package is, as far as things happen in R, then everything is written in R. The things that do not happen in R happen in GDAL, and GDAL anyway is further away and it's being called through SF and so on. Here's a little example that you see where the raster we get is the so-called curvilinear grid, so it's not aligned. It's not aligned with north and southing and so on, and you can also handle that, and it is associated with different times. And this is a little demonstration where you basically see a time series of these curvilinear grids, and we see a study area, which is the North Carolina boundary. And what we see happening is basically one of these hurricanes landing here, and we are now going to look at what are the precipitations, what are the maximum precipitations for each country by each time step. Yeah, and that involves basically intersecting all these raster cells with all of the counties. We saw the counties yesterday, and that gives you then this. And this is done basically by function called aggregate, which is also a base R method. It's basically in tidyverse. It is the sort of the contraction of a group by and a summarize. Yeah, you create groups, and then you compute something for each of the groups for all the variables. Yeah, and this contracts the two things. Basically, it says I have this precipitation, which is the three-dimensional, which is a raster stack of these curvilinear grids. Yeah, so a time stack of those. So you can see that data set here. Yeah, so it says untitled precipitation of the surface, blah blah blah, in kilogram per square meter is the units. So it takes care of measurement units that come from the netcdf file. Here's the netcdf file. It has measurement units. So we propagate these things. We see that x and y are basically the row and column index. That x and y are associated with matrices with the longitude and matrices with the latitude coordinates that basically tell me where each row and column is, right? That is what we see here. This is not it's not square and it's not north-south oriented, so it's curvilinear. So it says, okay, I'm a curvilinear grid. And I have a time dimension where you see that also time is 23 steps. I only plotted 6 here. And it is a regular one because it has an offset and a delta. You can see here that is this, by the way, visible in the back still? Can I show? Can also make it a little bit larger. It will make things easier. So we have an offset. So this is the time step of the first of the start of the layers, and then I have 23 layers that are 1 hour difference. Yeah, so we see here that we have for my time dimension we have a real time structure, just not like a number or something like that, but something that is actually POSIX CT, which is our native way to reflect date times. And we have a time step that is a diff time. Yeah? So it uses these R structures for handling time, which is pretty rich, and tries to reuse them. And we are then basically intersecting by this aggregate command. We are intersecting this funny raster stack of 23 hours with the North Carolina counties, yeah, which is just a set of geometries that are shown here that we also saw yesterday. And then, of course, for every county, I have, for every time step, a bunch of cells, and I need to say what I'm going to do with these cells. And I, for instance, could compute the maximum. Yeah, so this is the function that I'm now running on all of the cells that intersect with a county in this thing. Yeah, so I get a maximum precipitations for every county for every time step, and that gives me a vector data cube. Yeah, because here I get maximum precipitations for every county for a sequence of time steps. Yeah, so I have 100 counties and I have 23 time steps. Yeah, so that is a two-dimensional array, and it's not shown here. But when I run this, let me just run this. Let's see. It wants, of course, tidyverse to be loaded. Yeah. So I get my. So of course these things plot extremely slow, right? Because images that are rastering aligned with north-south go very fast. This is basically plotting every cell as a small polygon without a border. So that is why the plotting is so cruciatingly slow, but it is okay still. That is probably why I plotted 6 and not 23. And if you plot this on PNG devices, for some reason it goes much faster. So we see here this same image happening here, and this aggregation here. Of course, I need to load and see then. Let's see. Aha, okay, I have a problem here that my coordinate reference system is not the same thing. CRS. So one of them is WGS84, and the other one is NAD27. Yeah, they both are geodetic reference systems, and of course they're different datums. But I'm just going to override one with the other and ignore that problem. Let me just transform, do it a nice way. Let's see, ST transform to the CRS of precipitation. Yeah. So I'm doing I now did a datum transformation. And now the next step should work. Oops. This one. Right, so I get a little warning here. It says, although coordinates are longitude, latitude, ST intersects assumes that they are planar. Yes. So I do an intersection, yes, on geodetic coordinates, one called longitude, latitude coordinates, but doing it in geos, and it warrants. If I had said ST use S2 true, and I switched it to false, SF use S2, yeah, and then would have run this aggregation, it would not have complained, as you see here, right? Because I work with geodetic coordinates, I should do things on the sphere. Yeah, I get no warnings. Yeah, you get warnings here, which the warnings have always been there. Yeah, so I get rid of this. So that's a good thing. I get rid of warnings, actually, I think. And then I get these, so these 23 counties here, as you see, from the aggregation. So the intersection over a time series of raster stacks for a set of geometries, and I get for every geometry a time series, yeah, and this basically shows the spatial time series of the vector data. So, unsurprisingly, this object A is then also not an SF object, this is a stars object, because it has two dimensions. It has a dimension geometry, which are the 100 geometries, the 100 counties, yeah, the multi-polygon geometries, and it has a dimension time, because I did something for all the time slices. Yes, I gave a single geometry, but had a time series of rasters. So I get back a time series for each of the geometries. And so this is a vector data cube. Yeah, so remember that word. Yeah, it's going to be vector data cubes. And so vector data cubes, if you want to do anything with time or multiple bands and so on, and have a lot of points, then you need to organize that. You need to organize that dimension, and vector data cubes is one way to do that. Of course, you could wonder, like, how do I read or write them? And it seems that NetCDF and its successor ZAR are the two formats to do that. And the tooling is dreadful, but it can be done. Still, it's very curious about how far Xarray is in that respect to deal with geometries in NetCDFs. You can do so. That means you can store multi-polygons in NetCDF files. Yes. It's just, you know, they're clever people, the weather and the climate and forecasts people. They have thought things through very well. Okay, that was it. And now, what I wanted to do is sort of find out for each county, because you see this hurricane kind of coming over, right? Making a landing. So for each county, I would like to now sort out what is the time, at what time is precipitation at its maximum. Yeah, so that is, I have now a time series for every county. I could sort of get rid of my time. And one of the questions you could ask, at which time is this time series maximum? Of course, it would be easier to find the maximum. Yeah. Because you would say, okay, I have a vector, it's the 23 numbers, and return to me the value of the maximum, yeah, which is a single function, which is like here, I do in my aggregation simply max over a set. And now I do, like, I want to know a time, so I want to have the index, and then the index translated into the corresponding time. Yeah. So one of these 23 is at maximum. So I get, like, you know, like image 14, but then I want to have the time of that 14th image. Yeah? So this is a bit of, you know, slightly ugly code, as you can see here. in the sense that it's not, not maybe not extremely readable. But what it does is basically it gives me a spatial image where the a single geometry, a single map where the attribute that I'm looking at is time. Yeah, so it's a time. It has time as the attribute, which is the time of the maximum, and you can see that this sort of yellow are the latest, so that these inland counties have the later maximum precipitation values. So you can do these things. But you couldn't do it, you couldn't do it by doing a different, I think you couldn't do it by doing a different ordering of the aggregation steps or of the intersection steps, because I'm looking at maximum. Maximum is a nonlinear operation. If I would do kind of things like means, it doesn't matter in which order you average things typically, or quite often, you still have to think, but here it does matter. Right, so that is one thing that I wanted to point you out to, that we can deal with raster data and stacks of raster data and sets, whatever ordered along whatever dimensions, sets of raster stacks, stacks of raster stacks, stacks of raster stacks, and so on. No problem. And also stacks of geometries, like time stacks we have here of geometries, and there can be multiple dimensions associated to that. I also have in the book an example of two geometry dimensions where I basically look at a thing that I found interesting, where I look at go ahead. Yes, a good moment. Yes.
The aggregate function parameter accepts any kind of function, even one that I can write on R, or is it a basic function?
No, any function. Yeah, any R. So that is right. That is functional programming, right? So it assumes the function needs to accept the vector and return a scalar. Yeah, that is what happens. And you can also pass arguments, right? So if my here, where is my aggregate? Here, if my precipitation data set would have contained missing values, then of course max would all the time have given missing value if there was one of the values missing. And that you can add, and for instance, comma na.rm is true, which is an additional argument to the function max. Yeah, so you can parameterize these functions further, but you can also write custom functions. And I think I had a custom function here. Yeah, so here I have a custom function index max, which gives me which uses which.max, which is the index of the index of the maximum value, and takes care of missing values, and uses that not in an aggregate but in st_apply. And st_apply basically applies functions to dimensions. Yeah, so st_apply is basically modeled after apply. Apply is, I hope that people know apply. Apply is works on arrays and does operations over dimensions. Yeah, so you could do row-wise maximum, column-wise maximum, and some things like that, or arbitrary functions in rows, column, or even sets of dimensions in higher dimensional arrays. I guess that is pretty much the same thing as what NumPy does. And this st_apply basically wraps this whole thing, and takes care of the dimensions, the dimension attributes of your stars objects. Yeah, so does the same thing, does the apply to the arrays, but takes care of finding out what the dimension attributes, what happens to them. Yeah, whether they disappear or get reduced or whatever, or remain. Yeah, I was looking at this example of two, then maybe it's not so. Yeah, here is an example of a vector data cube example where we have This is air quality time series for different stations. Where you see here, this is the so-called Hofmüller plot, where we have, oh no, it's not a Hofmüller plot, and this should be a coordinate. It's a station identifier. Another example that I used here, I think, is origin destination matrices. Yes, where we have origin destination. This is from a data set that Loveless, Nobelsat, and Munchow used in their book Geocomputation, the first edition. And where we have movements of the number of movements from an area to another area by means, yeah, by car, bicycle, or foot, something like that. So we have basically it comes as a long table where we have the origin, the destination, the total number of movements, the number of bicycle, foot, car, and train movements, and I reworked that essentially in a raster data, vector data cube, where we have things arranged to a 102 by 102 array by 4 modes. Yeah, so we have the full matrix, the full origin destination matrix, it's filled with zeros when there are no movements, and filled with data when there are movements. Yeah, this table, of course, only has the movements. Yeah, it doesn't have the zeros because there's a lot of things where nothing happens. So this is somewhat, you know, exploding the data somewhat in the sense that it adds all the zeros. But here you see an example where I have origin and destination, where I have 2 spatial dimensions, each associated with the same set of geometries, the multi-polygons of the origins and the destinations, and then have a mode. And you could have this by time. If you have this by hour or by 5 minutes or something like that, you would add another dimension. You could look at when and where are the pedestrian movements at a maximum or something like that. You could do these kind of queries. You can also kind of do all kind of plots, like if I'm interested in the movement to and from a single, this seems to be the busiest district, and if I want to see where everyone comes from, going here, then you can see and split that by different attribute. And the code is essentially very very simple. It's a slice here on this third destination. Yeah, this is the 33rd destination. The second dimension follows after second comma, and you see here the movements going on there. So, and then you can do all kind of aggregations. For instance, some like the total number of movements across all modes, or you can do other aggregations. For instance, sum by destination and get it sum of destinations and get all the origins in the modes and so on. Yeah, so you can, in that sense, you can do relatively simple things that, of course, you could also do by the original data set, by the original table. But the analysis looks very much different, yeah, in the sense that in my book, at least, these are sort of relatively natural array data, and thinking about these things as arrays sort of a nice way. How am I with the time? Very bad. So yeah, there is one thing that I also promised to talk about, and it's the package sftime. And before I run out of time, there's the package sftime. Sftime is an extension, basically is written by Henning Teigner, who won the OpenGeoHub Hackathon Award 2 years ago, by the way, and is now a very prolific R developer, but also a researcher. And he worked on this package together with Ben and me, and that basically deals with irregular time data. Yeah? So, for instance, here is a data set that comes from the package STPP, which is the cases of foot and mouth disease, FMD. So this is an epidemiological or veterinary data set where we have the coordinates and the day of a disease outbreak, an outbreak of foot and mouth disease. And you can basically handle this and say, okay, these are the points and these are the times, but these data are irregular, right? We have a data set, let me see, here's the plot. where you see the North Cumbria polygon and the points of the outbreaks ordered by time, and you see that these are the sort of the farms where it happened, it is essentially it's not a trivial array in the sense that it doesn't have more than one dimension. Yeah, it's just a sequence of events. One-dimensional sequence of events where every event has an associated space and time. It's not something like measurement stations where at one point you have a time series of measurements, like what you would have with like air quality measurements or something like that. There you have multiple dimensions. You have a time series for every point. This is just sort of points, irregular points in space-time. In exactly that case, irregular points in space-time is covered by the SF time package, where we extend basically SF objects, which have the geometries, with a time column and register where the time column is, so that software can then query the time and say, what is your time, right? Are you in time, irregular time object? Yes, and give me then your times back. Yeah, so that is tooling that you need for things like spatial temporal interpolation and spatial temporal point process density. Here's an example where I basically aggregate these things and count them for cells of 20 by 20 kilometers or whatever miles. This is the UK. I have no clue. And then basically count them for different periods. Yeah, so that so what you typically do is do some kind of density over space and time and model that. This is sort of a poor man's density where I count instances where I have 30-day periods. Somewhere I compute 30-day periods, and for these 30-day periods, I count the number of instances for each 20 by 20 kilometer block, and get that as a stars object. Yeah? So this is just in conjunction to stars, where I have temporal spatial data associated with time that are not, that form not arrays, but that are basically irregularly distributed in space and time, and that you're then typically going to analyze in ways, either by spatial by spatial interpolation, if they're continuous variables, if they're field variables, or if they are objects, like here the disease outbreaks, where you're going to do a point density, a point pattern density in space and time, and model the density surface as a function of space and time, and again display that again as something that is an array in space and time. Yeah, so this is an example that I brought up that is part of the website of today's course. Let me see. This is the example that I brought up here, which is called time. Yeah, so you can look at that and download the Quarto file and run it as an example, as an illustration of how to use the SF time package. So it's a relatively simple class. It just adds time to geometries for things that are further not further structured in the sense of array structures. And we're slowly building the things with spatial temporal interpolation and GSTOT, and with sort of handling them and integrating them with stars and with array data to make that more mature. So that was what I wanted to say. Are there any questions? And sorry for talking into the coffee break. Yeah, go ahead.
I guess for indexing stars objects, I'm used to working with data frames, less comfortable with multi-dimensional arrays. So how do you keep track of how to index across all of your dimensions, like which ones come in what order to actually get the data?
Yeah, that's a good question. How do you deal with indexes on the different dimensions? And there I actually use the R mechanism. Yeah, so R's own indexing mechanism, which is very strong. So so arrays are, so arrays are really sort of simple things. Yeah, I could have an array of 1 to 27, which it's three-dimensional, like this, and I can index that and say, well, I can use the first, if I will, and I get sort of the first slice, or I can get this first slice in the second dimension, or I can get the first slice in the third dimension. And it stars basically copies that model. Yeah, so on startup, you can use the same index, just there's one extra index, one extra comma, because we also have attributes. So the first indexing item is that of the attributes. Yeah, so there's one, you just have to think, okay, there is one extra comma I have to when I do this kind of indexing. When I have this last two slices, I get this kind of thing. So you can do that kind of indexing. It's simply copied to the array. Well, it doesn't mean it's not simple. It's a hell of a job, but that can be done. Yeah, you can capture that and pass it on, so to speak.
The first one is always your attributes, and then after that, how do you know like which one is like? How do you know which dimension each slot corresponds to? You have a bunch of them.
Yeah, well, let's try this. So I have. This is maybe not such. I don't know if this is very well working for curvilinear grids, but in principle, let's look at the Landsat 7 data set, which is here. So I have a single attribute here, which are my pixel values, and I could index that by saying I want for X, I want to have the first 20, and for Y, I want to have the first 30 cells, and then for the band, I want to have band 4, 5, and 6. Yeah, so something like that, and then plot that, and then you see that it's being plotted. Yeah, so there's 3 bands 4, 5, and 6, as you see here, and then these 20 by 30 sort of upper left corner of it starts upper left, and it can sort of do arbitrary ranges. I think I can even leave out rows and columns, but it becomes messy with the dimensions then, of course. Yeah, there's a lot to say also about that. If you have large data sets and you want to plot them, I think I went here to the stars data set articles. It's probably in the proxy object category, and that basically explains that here is a Sentinel-2 data set that is with 4 bands that is plotted in some way, and you see here that if I do that, then it gives me the message I'm downsampling here with a factor 18. Yeah, so the plotting routine here looks at, okay, how many pixels are these? How many sort of subplots do I have? So 1 pixel is then on my page equivalent to 300 meters. Well, these are 10 meters pixels, so I can sort of downsample. I can ignore most of this. I'm never going to get these. Every image is 10,000. The original data is 10,000 by 10,000. So it downsamples that and basically first grabs the lower resolution version of this and then plots this. Yeah, so there's a lot of things that it wouldn't make any sense to plot more than this. Yeah, if you would plot more than this, you would just take much longer, and you would wait for 15 minutes for the plot to return. And here it took 2.5 seconds. What it essentially does is that it's passed on to GDAL, but it reads these overviews. Yeah, these data sets come with overviews of lower resolution, which are of course much smaller, and reads those. So this is one trick to do things at lower resolution. And these proxy objects also have this effect that if you do computations on them, like compute the NDVI, it's postponing that. And if you then plot the NDVI, it will basically say, okay, it's an NDVI, so it doesn't matter spatially, it doesn't do any spatial operations, it's just on the bands, and then looks at, okay, I can compute the NDVIs on the downsampled version, so I still have a quick plot of. This is basically what we learned from Google Earth Engine, that when you want to see something, it's typically much lower resolution than the original data, than the full resolution data. So if you do computation, you typically only have to do the computation on the lower resolution for the extent that you're looking at. And so there is these kind of smart things, or at least an attempt to do this in a smart way. And then is sort of, this is another thing, but this is works also with kind of with indexing, yeah, that you basically say, you know, I don't want to have a sub region, but I want to have the same area, but then at a lower resolution and get these things. So you can do that too. Also with multi-dimensional, I've spent a lot of time in reading multi-dimensional arrays through this multi-dimensional API in GDAL, so that you can read netCDFs and ZARs and so on. Very big data, but read them at a lower spatial or temporal resolution, and then you get things that you can look at, which, you know, summarize it very well in very short time. So that is a very useful sort of thing for data analysis. Good. Any other questions? Thanks. Good, then I suggest we go for the coffee break. Thank you for your attention. Shall I just plug this out here?